So now I'd like to talk about Maclaurin and Taylor series. First, let me kind of introduce what they are. We've already talked about power series, and we've taken functions, certain functions, and created power series for those functions. So the question we want to ask ourselves is, can we do that for any function? Can we always create a power series for functions? And the answer is yes. Let me show you how we do it. Suppose I can write a function as an infinite polynomial. So I've got some coefficient, a sub naught, a sub 1x, a sub 2x squared, on out to infinity. It keeps going. So we need to figure out what these coefficients are. Well, if I plug in 0, everything disappears except a naught. So I know that a naught is f of 0. Well, how do I get at a1 in the next one? Well, if I take the derivative, a0 is gone, and I'm left with just a1, no x, and then all this other crap. So now I have this. If I plug in 0, the only thing that survives is a1. Cool. Let's try another one. Second derivative. I plug 0 in. This time I have 2 times a2, so I actually have to solve for a2. So a2 is equal to the second derivative with 0 in it over 2. Let's do another one. So the third derivative. That gives me 2 times 3 times a sub 3 plus 2 times 3 times 4 times a sub 4x, and on and on and on. Plug 0 in, everything falls away except for the 2 times 3. So I solve for a sub 3 and I get the third derivative with 0 plugged in over 3 factorial. Hopefully we can see the pattern now. When I take the next derivative, this is what's going to survive, times a4. And this is 4 times 3 times 2 times 1, 4 factorial. And when I do the next one, I'll have 5 times 4 times 3. This 2 will come down, so I'll have 5 factorial. So I have a naught is f of 0, a1 is f prime of 0, a2 is f double prime of 0 over 2, a3 is f triple prime of 0 over 3 factorial, and a4 will be the fourth derivative over 4 factorial, etc. So I can write this series as summation from 0 to infinity of the nth derivative with 0 plugged in over n factorial times x to the n. And this is a Maclaurin series. The difference between a Maclaurin series and a Taylor series is a Maclaurin series is centered at 0. So we have a Maclaurin series is centered around 0, and a Taylor series is more generic. It's when it's centered around any other number. Officially, Maclaurin is also Taylor, but we want to give Maclaurin his due. So he gets the one that's centered around 0. And this is a Taylor series that's centered around a. But for now, in this class, we are going to concentrate on just Maclaurin series. So let's try to find one. Let's say we've got f of x equals e to the x. We need to look for a pattern for our derivatives with the 0 plugged in. F of 0 is 1. Cool. First derivative. It's also e to the x. So when I plug in 0, it's still 1. Third derivative. Fourth derivative. You get the idea. All these are going to be 1. So all I have to deal with is the factorial. So the Maclaurin series for e to the x is a summation from n to infinity of x to the n over n factorial. Before we try another one, let's look at the radius of convergence. For what x's will this series converge? Well, you have a sub n times 1 over a sub n, so x to the n plus 1 over n plus 1 factorial times n factorial over x to the n. The x's will cancel. I'm left with just an x on top. My n factorial on top and my n plus 1 factorial on bottom, I'm left with just n plus 1 on bottom. So now I'm taking the limit as n goes to infinity of x over n plus 1. Well, as n goes to infinity, this sucker goes to 0, which is always less than 1, which means my interval of convergence is the entire real line. Next one. Find the Maclaurin series for f of x equals sine x. Okay, well, f of 0 is 0. The derivative of sine is cosine. F prime of 0 is then 1. I take the next derivative, I get negative sine, and negative sine of 0 is 0. Okay. Third derivative, I get negative cosine. Plug 0 into that, I get negative 1. And when I take the next derivative, I'm back where I started with sine x, and I plug 0 in. And it will keep going through this 0, 1, 0, negative 1, 0, 1, 0, negative 1. So let's write out the first few terms and see if we can come up with a pattern. So 0x, 0 x cubed over 3 factorial. The next one is positive x to the 5th over 5 factorial. So next I'll get negative x to the 7th over 7 factorial, etc. I'm only getting the odd powers, and the power on top matches the factorial on the bottom. So my Maclaurin series is summation from 0 to infinity, -1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. Now, what about the radius of convergence? This one's going to be a little ugly, but that's okay. So we've got this massive grossness. I've plugged n plus 1 into this expression. So I get 2n plus 1 over 2n plus 1 factorial times 2n plus 1 factorial over x to the 2n plus 1. Let me simplify this before I try to do canceling. So the top becomes 2n plus 2 plus 1, so I get 2n plus 3 over 2n plus 3 factorial. And then I still have the 2n plus 1 factorial over x to the 2n plus 1 in the next term. So x's will cancel. I'm left with an x squared on top. I have 2n plus 1 factorial over 2n plus 3 factorial. So I've got the two extra terms. I have 2n plus 3 and 2n plus 2, and then all the others will cancel. So what I have here is x squared over 2n plus 3, 2n plus 2. The limit of that is 0 because the bottom is going to go to infinity. And 0 is always less than 1. So again, interval of convergence is the reals. Let's try one more. Cosine. Is cosine going to be nasty? That was a lot of work for sine. Do I really want to do it for cosine? Well, we have a trick. We don't have to go through all that shit this time. I know that sine x equals this mess because I just derived it. And the derivative of sine is cosine, so I'm going to take the derivative of that. So now I know that cosine can be written as the summation from 0 to infinity, -1 to the n, x to the 2n over 2n factorial. It's going to have the same interval of convergence because we did that with the power series. We know that when you take the derivative or integrate, it will have the same interval of convergence. Now, why are we doing this? Well, Taylor series and Maclaurin series are good ways of modeling function, especially in, say, a computer. When you have a computer and it needs to calculate sine of something, it uses a Taylor series or Maclaurin series. Let me show you what's happening. So let's see how good this estimate is. If I let f of x equal sine x, and then I'm going to let m of x just be the first two terms of that Maclaurin series. See if it's any good. Well, notice it actually estimates pretty good between here and here, but also only did two terms. What if I add a couple more terms? Now let's plot these two functions and see how close they are. That's pretty good. I mean, it goes a little weird at 5 and -5, but in the center section, it's kicking ass. It's pretty close. And imagine if I go a little bit further and a little bit further. And if I wanted to model a different section, I would just use a Taylor polynomial centered around where I want to look at. So these are giving us pretty good approximations. So we'll be doing these in class and trying to come up with more of them.